Okay, so in this video, I'll be going over a couple of sample problems using the calculus variations and the first variation thing that we saw in the last couple of videos. So this first one won't really have much physical significance, but it's some nice math. And then the other ones that I'll go over in this video will have more physical significance. And the thing is that it doesn't explicitly depend on the independent variable x like I have here. So I'm gonna, before I go through those examples, I'm gonna derive something called Beltrami's identity, which allows you to do the math a bit easier. And also, just as a forewarning, for this video and all the later videos, I'll be writing partial derivatives using subscripts. So the partial derivative of f with respect to y, for example, is f sub y, and the partial derivative of f with respect to y prime is f sub y prime. And I will start doing like the partial derivative with respect to like y prime and stuff, instead of changing that to z. So just to reiterate some of the ideas from the previous videos, we have some functional of y where you plug in a function y of x as an input, and it'll give you some real number as an output, and that real number is given by this expression. And so in this case we have that j of y again is equal to some integral of some expression that looks like this. So you have some function of three variables, and in this case the function is f is equal to x squared z squared plus y squared. Yeah, so if you just plug in y prime for z, then you get back that expression up there. And so in the previous videos, we saw that we want to set the first variation equal to 0, and that allows us to derive the Euler-Lagrange equation, which is f sub y minus d dx f sub y prime is equal to 0. So you're taking the derivative of this function with respect to y, and then you're taking the derivative with respect to y prime, differentiating that with respect to x, and then setting that equal to 0. So this is the Euler-Lagrange equation, and so let's use that to solve this out. So the derivative of this with respect to y would be 2y, because this first term doesn't depend on y explicitly. And then the derivative of it with respect to y prime, so it's minus d dx. So the second part doesn't depend on y prime explicitly, so now we treat y as being constant, and we differentiate with respect to y prime. So that'll be x squared times 2y prime, and that is equal to 0. So the first thing you notice is that you have like a 2 here and 2 here, so you can just sort of get rid of those. And now you can expand this derivative by using product rule, and you get y minus, so you take the derivative of the first part, which is 2x y prime, and then you take the derivative of the second part, so that'll be minus x squared y prime, or y double prime. So the second derivative of y with respect to x. And so we can rewrite this as x squared y double prime is 2x y prime minus y is equal to 0. Now, notice that you have something times x times some derivative of y with respect to x. And so here we have x squared times the second derivative. Here we have like x to the power of 1 times the first derivative. And here we have x to the 0 times just your function. So when you have something that looks like this, a good guess for a function is y is equal to x to the power of r for some value r that's to be determined. So if we plug that into here, minus y is just minus x to the r. And then minus 2xy prime, so y prime is just equal to r x to the r minus 1. So this will be plus 2xr x to the r minus 1. But then x times x to the r minus 1 would just be x to the r. And then y double prime is equal to r times r minus 1 times x to the r minus 2. So then if we go back to here, that'll look like r times r minus 1, x squared x to the r minus 2. And again, you're multiplying x squared times x to the r minus 2. So that will just go away, and you get x to the r again. Now you can factor out in x to the r and set this equal to 0. So that'll give you r times r minus 1 plus 2r minus 1 x to the r is equal to 0. And now this must be true for all possible values of x. So if it's true for all possible values of x, then that means that you can sort of ignore this, and this whole term must be equal to 0. And if you want to think about that a bit more rigorously, you can like say, okay, x equals 1, x equals 2, x equals 3. If all those must be 0, then this thing over here must be 0, because x to the r is not always equal to 0. And so here we just need to solve for this is equal to 0. So we have r squared minus r plus 2r minus 1 is equal to 0, just r squared plus r minus 1 is equal to 0, which gives us 2 roots of r. So r is equal to -1 plus or minus square root of 5 over 2. So now looking back to here, we have two possible solutions. And because this is a linear differential equation, we can take any linear combination of those. And so we have y is equal to a x to the 1 plus root 5 over 2 plus b x to the 1 minus root 5 over 2. Okay, so now we're going to go to our boundary conditions that I did not say in the beginning, but I should have. So we have that if you plug in x equals 1, then y should be 0, and if you plug in x equals 2, then y should be 1. So the first one says that y of 1 is equal to a times 1 to the power of something plus b times 1 to the power of something. So here 1 to the power of anything is just 1. So this is just a plus b, and this is equal to 0 because of our boundary condition. And so that means that a is equal to -b. And y of 2 is equal to 1, so I mean that y2 is equal to a times 2 to the power of 1 plus root 5 over 2 plus b times 2 to the 1 minus root 5 over 2 is equal to 1. And so for example, if you want to solve for the coefficient of a, then you set b is equal to -a, so you change this to minus a, and you say that a times 2 to the power of 1 plus root 5 over 2 minus 2 to the power of 1 minus root 5 over 2 is equal to 1. And so you can just invert this on both sides, and you can say that a is equal to this inverse. And then you can just say that this is the same thing as -b, because b is equal to -a. And now you can put that back up here, and you finally get, let me erase that, y is equal to 2 times 1 plus root 5 over 2 minus 2 times 1 to the power of 1 minus root 5 over 2 times x to the power of 1 plus root 5 over 2 minus x times 1 minus root 5 over 2. Okay, so that was just a bunch of math, but to say what all that was, we're considering all of the functions on the interval 1 to 2, which, oh wait, this should actually be the integral from 1 to 2 because that's what our boundary conditions are. So we're considering all functions on the interval 1 to 2 that satisfy that on the left endpoint, which is 1, the value is 0, and on the right endpoint it's 1. And we're looking at this functional, and we want to see what function minimizes that functional out of all the curves that satisfy this, or not necessarily minimize, it could also maybe maximize it. And then we go through this process of solving it, setting the first variation equal to 0, getting a condition on y, and then solve it out to find that y is equal to this function. So yeah, now let's go through some other examples and derive Beltrami's inequality, or Beltrami's identity.